So we are beginning chapter 18, talking about stars. We have moved out of the solar system officially, talked about our sun as an example of a star, but now we're going to talk about other stars, the size and number of stars. So what variety should we expect? And of course, we're looking at the HR diagram. We're going to be looking at that a lot. More on it later. Okay, so to get things started, we want to talk about a common type of star system that is different from our own solar system. And that is binary stars. This is when two stars orbit around a common point, the center of mass of those two stars, essentially the balance point of the two stars. It has a technical name called the barycenter. So that would be the point of orbit. And here we have an example of a binary star system. Okay, we have Albireo, I think I'm saying that correctly, Albireo A and Albireo B, two different stars. We can see that with a good telescope, we can clearly see the two of them side by side. All right, they have the characteristic lens flare effect that nearby stars have compared to the more distant stars that are not flared. That's how you can tell that the star is near relative to the background. But the question here is a review question. Which is hotter? Do you know how you would tell? What's your answer? Doesn't have anything to do with them being binary, by the way. So, but it's a review question, something we talked about before. Just looking at this image showing visible light, it's a visible light image, which of these two stars, A or B, is hotter? Thumbs up for A, thumbs down for B. Put it in the chat. Okay. Angelina says B. All right, Laura agrees. Okay. All right, so my guess is that you were thinking the color, right? You said, oh, it's got to be the blue one. And if that's the case, then you are correct. Okay, the blue star is hotter. This sort of the yellow star might be the temperature of our sun, but some stars shine with the peak towards the blue end of the visible spectrum, and they are by far the hotter star. Okay, good. Okay, so here is another example, BHB 2007, right? We actually see the two stars here. Okay, in this case, I think there might be like some sort of a planetary disk around them. It also might be that one of them is pulling matter off of the other. If the mass of one is much greater, and therefore the gravitational tug is much greater compared to the other, then there'll actually be an exchange of gas. So there'll be this kind of like shared plume. We see that represented artistically here. And what ends up happening with these binary star systems is sometimes these very dramatic and interesting relationships. In this case, the star is named Mira. We'll talk more about this later, but this actually has to do with one of the stars essentially already being dead and the other star still being in its main phase of life, and the dead star being so much denser that it's able to pull off the gas from the surface of the other star. And the reason this is actually fairly common with binary star systems is that to begin with, they were different masses. And we'll learn that the starting mass of a star dictates how long that star lives. So it was predestined how long each of these stars would remain as a star before shifting into a different astronomical entity. And that means that lots of times those two lifespans don't match up. It'd be unlikely that their two stars just happen to form with identical amounts of mass. It tends to get unevenly distributed, okay, when these common binary star systems form. So that means that this ends up having this then later stage of interaction between the dead star and the star that's still alive. Jasmine, did you raise your hand?
Yes, I did. So for clarification, which star becomes the dead star? Are they both like is one of them already technically dead, or
Yeah.
does it the binary become dead?
The binary system would still have one living star, which
Mhm.
we would say, one star that still is undergoing fusion, which is the condition for quote unquote life, and then one where
Mm,
there is no fusion. And so the dead star in this case is the blue star,
okay.
and then the orange reddish star is the living, maybe main sequence star, maybe red giant. And
Okay, that's why I thought it was A because it still takes on life, technically speaking, right?
so
And
you thought A for the hotter one?
yeah, because of the sun. That's what I was like. You know how like kind of like even when you have like the moon cycles and stuff, it's technically the sun shining through, so there's still some sort
Yeah.
of light behind it.
Yeah, it's reflected light from the moon. Yeah.
Yeah.
Yep. Yeah.
Okay.
Yeah. So I guess the idea here is that we as we moved out of the solar system, we're going to learn about all these different types of stars, and some of the notions that apply to the solar system will get recalibrated when we talk about stars. And honestly, like just this image is really like to unpack it is a lot of the stuff that we haven't talked about yet. So don't if it doesn't make sense yet, it shouldn't, because like what the heck is main sequence? I mentioned it briefly before, right? When we talked about the sun. It's by the way, it's fusion of hydrogen into helium. But then I said it might be a red giant. Well, what defines a red giant, And so these are all things that we'll be talking about when we talk about these rules, life cycles, and processes of stars. And they're not terribly complex, and it's kind of fun to be able to categorize them and think about sort of these like flow charts of state life stages and so on. So I think many of you will find it quite interesting. Right. But yeah, this is and I don't want to like hide information either, but this is stuff that don't expect to know it right now. But the name of this type of dead star is a white dwarf. Okay. And it could be a neutron star, but it wouldn't look like this. But this type of interaction is a white dwarf and a normal star. Oh, yeah, go ahead.
Sorry, so one more question because now you're bringing up the dwarf thing.
Yeah.
Because I know, like Pluto, they considered Pluto a dwarf planet, which is why they no longer acknowledge it as a planet.
Mhm.
So anything that is, it's almost, is it like sort of like the human body sort of thing going on? Like it's kind of like saying, like, okay, well, if this
Oh.
has a deficit, then you no longer acknowledge it.
Yeah, although I think hopefully we acknowledge people that have dwarfism.
Yeah.
But yeah, I'm like I mean, there's a lot of prejudice. But yeah, so with planets, that's clear cut that like a dwarf planet is not a planet, It's in white dwarf, that's also true. White dwarfs are not stars. So, which is funny because sometimes they're called white dwarf stars, but in a technical definition, quite similar to, saying, oh, a dwarf planet is not a quote unquote planet. But what kind of clouds the issue is that there's also something called a red dwarf, and red dwarfs are stars, no question. So it's not as clear cut as you might like. But white dwarfs are indeed not stars, but red dwarfs are. Again, we will talk about this more, I promise. Okay? Okay, so let's, get to the content and we'll get to all the names of stars as we go. So binary stars. Um, they're they're super important because they end up being really a great way for scientists to study stars because the way they orbit each other, they allow for calculations that you couldn't make if you just have one star. So go back to think about like Kepler's laws and the way that scientists can use those laws and measure things like time, like orbital period, in order to calculate radius, and if you know that, then you can get mass and so on. So they're wonderful tools. They're like assets for scientists. And so that's why they get a lot of focus, maybe more than you might think that they would deserve. But they're also, what I want to stress is how common they are. Half of stars in the Milky Way galaxy are part of a binary star system. So it was like a coin flip in a sense that our sun is just by itself. It's just as likely that the sun would have a twin, another star that it orbits. And not and maybe that they're both like, totally alive and just orbiting each other without disruption. So it's just a very common system for stars. Anyway, the types of stars, the types of binary star systems that we're going to list here have to do not with the life cycles of stars, but instead with how we see them and how we can measure them. So there's something called a visual binary. And a visual binary is when two stars orbit in such a way that we can see the orbit like in a plane. So we could observe the orbit over time by taking like a picture every week or something and actually see the stars move as they orbit some shared point, right? So maybe they're orbiting around the center, right? And so we could just track their orbit and make observations from that. So that's what's meant by a visual binary. You can distinguish them as separate objects in a picture, usually a visual image picture taken with a telescope. By eye, good luck. I don't think any of them are really naked eye visible, but at least with a relatively small telescope, you could see some of them. Okay, so looking head on. Now, they might not be exactly head on, right? Maybe your view of them is a little bit kind of like from an angle. So that could be the case here. Like imagine like, this is sort of like a 3D picture where you're looking at it from above, but also it's sort of projected out away from you. And and we can see that with the velocity shown here potentially. And so, you can observe that orbit, observe the velocities, and make calculations from them. Again, so crucial because it lets scientists find out things like the mass of the stars. Okay. And so you can have, mass differences between them. So you can have like a star that is a main sequence star, and then have a companion that is much smaller than it. So that's kind of the more common case, because just in terms of like just full on like randomness of the universe, it's more likely that when you start accumulating mass and when two stars form and they both start pulling in mass, that one of them is bigger from the beginning and pulls in more mass and therefore has a head start and is able to pull in even more mass, and then it ends up being much bigger. It's sort of like this like, I guess it's real different than human twins, right? Where there might be one that's a little bit bigger, but kind of like the way the homeostasis of the human body kind of keeps giving them like fairly similar nutrients. Well, the harsh physics of accretion of matter doesn't work that way, and so if one starts bigger, it ends up being much bigger. So you end up with usually a pretty big disparity between the masses, and that's what they're pointing out here in terms of like what's going to happen with their percentages of mass. So we have like average percentage of mass in the larger star. So like 97% of the mass in the larger star in this case. There's a lot of information in this table, and I don't want to spend too much time on it, but I do want to like point you to what like at least like how you would read it. Okay, so let's look at this first row. So this is referring to some star that's on the main sequence, a term we keep using a lot and hasn't probably gotten the formal definition that I would like it to have. But as I pointed out back in chapter 16, it's any star that burns hydrogen, quote unquote burns, right? Fuses hydrogen into helium, like our own sun. That's a main sequence star. It's by far the most common type of star. Okay, so if you have a main sequence star that has a mass that's 1/10 or less the mass of the sun, then that's what this row is describing. So these are small stars. These are stars that are 10 times smaller than our sun, which is about not quite the minimum, but about as small as, towards the smallest end of stars that exist. Okay, these are small stars. About 20% of them. So the average, or actually here we have, so the average number of companions is 0.22. This is kind of hard to read because what does it mean like to have 0.22? Well, it means that that on average, one of these stars has a fifth of a companion. It's like the same way that, we talk about the average family having 2.5 children. No one actually has 2.5 children, right? It's an average. So it's saying that, the average is to have a fifth of a companion. And that literally means that 22% of stars with this mass, these small stars, have a companion. So about 1/5 of the small stars have a companion. And when they have a companion, the percentage of mass in the larger of the two is by far most of the mass in the system. So whenever one of these stars is paired up with another, well, then the one it pairs up with actually ends up being really big, and it's going to be the tiny little tag along, and they're going to orbit each other. And in that case, it's almost like the small one orbits like a gas giant because the big star is so much bigger, right? I mean, this is almost the kind of mass disparity that we see in our own solar system, where the sun is 99.9% of the mass. But of course, this is 97, so it leaves 3% available. Still, not a lot. Okay, so that's how you read this table, and so you can tell there's really a lot to discern here. Is I'll point out as you go down. Let's look at stars that are a little bit bigger than our sun. So stars that have a mass that's 1.5 times the mass of our sun, up to 5 times the mass of our sun. In this case, they usually have one companion, and a full 50%, and perhaps more, so this is a lower estimate, of stars in this size range have a companion. Like I said, right? They tend to have companions. And in that case, the average percentage of mass in the larger star is actually only 55. So this is a case where the two stars are balanced. They tend to be about the same size. So this is an interesting type of binary system because it's not really going to lead to that whole case where one star dies young and then ends up feeding off of the star that's still alive. I know I choose the wording on purpose, right, to kind of make it sound like zombie stars. Of course, we don't know. I haven't explained the rules about which stars die young. If you're thinking it's the small stars, I don't know. Sometimes it's easy to think that. It's not. It's actually the bigger the star, the faster they burn out and the shorter their lifespan. And it ends up being really dramatic. The biggest stars don't live very long. They live a tiny percentage of how long, like a smaller star lives. So they would absolutely, transition to some other phase and then end up changing the binary system. Okay, so far, visual binaries, summary of data, lot to take in. Another type of binary system. Again, it matters because of the technique that can be employed to study something called a spectroscopic binary. I'll explain what that is, and how these type of binary star systems let astronomers find mass. So what is a spectroscopic binary? It's two stars that orbit around a common point. So that part's just binary star system, okay? But a spectroscopic binary can be distinguished from their spectral lines using the Doppler effect. So in this case, the orbit isn't in a plane that we can see. Instead, the stars are orbiting each other with one of them always in front of the other relative to our line of sight from Earth, or behind the other, or to the side. But we mostly care about when they're in front or behind each other, okay? And actually also, never mind, we also care about when they're to the side because that's when they're going to be moving either towards or away from us. But the point of view is that, the point, and also the point of view, is that we can't see them actually orbit each other because our line of sight doesn't allow for that. We can only see them orbit each other when we're literally looking down on the solar system, on that other solar system, right? That external solar system. Okay, so Doppler effect. Do you remember what it is? So stars A, B, and C are identical and emit black body radiation with the same peak wavelength. So let's say we already know that all three of these stars all have the same surface temperature. Maybe they all have 5,800 Kelvin photospheres. So they all produce a peak wavelength at around 480 nanometers. The waves drawn are the peak wavelengths of the stars as seen from Earth. But they're not, all of a sudden, they're not all the same. Why is that? Well, the wavelengths are shifted due to the motion. Because even though they may all be the same star, and if they were all at rest, they would all look the same to us. If they're not at rest relative to us, then they don't look the same. That's what the Doppler effect is. And if we know that star A is stationary and producing its peak wavelength, right, kind of in the green color, which star has its light shifted to a longer wavelength? The one that is showing a tighter pattern, or the one that's showing the extended stretched out pattern? Well, not hard, as long as you remember what a wavelength is. This one literally looks longer, right? So C has the longer wavelength. It's redder. We say it's red shifted. So then if star C is moving, is it moving towards or away from us? To get this type of shift, is star C moving away or towards? Who remembers? All right. Yep. So yeah. Isabel gave us the answer. Thank you. But then what about this one? Towards or away? Okay. Tree says towards. Everyone agree? All right. So star C with the longer wavelength, the red shift is moving towards. Sorry, but it's not. And stop and think about it. Maybe remember the rule. It's things that are moving away that have the red shift. So star C has to be moving away in order to have a longer wavelength than star A at rest. Does that make sense? So I know, a lot of you put towards. I just want to make sure that, you see, okay, got them mixed up. That happens. But yeah, and that was the purpose of reviewing it, to make sure that we're good on the rule. Because, it's one thing to see it and then not really use it for a week or two, but now we're going to be using it again. Okay, so we got a example spectrum right here for the star at rest, which is star A. And then they ask, which is the spectrum of star C? I won't check chat, but take a minute and think about it. So now we know that star C is moving away. We know it's red shifted. And all of that is fine, but astronomers don't see, a longer, wave like this. What they see is spectra like the one shown here. So that's why we want to be able to relate the spectrum change to the wavelength change, to the redshift. So in other words, which of these two spectra is redshifted relative to the rest spectrum? Well, it's the one that's everything's moved towards the red direction, right? So it's this one here. This is the redshift. And redshift corresponds to motion away. So all this matters because of these spectroscopic binary stars. And you can see where the term comes from. They're called spectroscopic because we're talking about their spectra. That's how we view them. That's how we know them. So two stars over the common center. All right, so the spectroscopic binary can be distinguished from their spectral lines. In reality, the spectra are complex. All right, both stars are moving. There are two oscillating spectra because they're never, just going to stay redshifted or blue shifted. They're going to vary, right? They're going to be redshifted for a certain period of time because they might have an orbit that is months long. They might have an orbit that is years long. Sometimes their orbits can be really short if they're close to each other, just a few days. All right, but generally not that long, right? Astronomers don't have to wait too long to get their data, and they're going to see a cycle of shifts because, of course, the motion is going to correspond to some sort of cyclic motion. One star sometimes moving away from us, sometimes moving towards us, and we're essentially at rest, right? Sure, we are orbiting the sun, but that distance is so small compared to the distance that relates to these spectroscopic changes that it might be accounted for in calculations, but for our purposes, we can ignore it. All right, absolutely, we're going to see varying shifts because sometimes we're going to see all of the motion. If you think about that point of view, because sometimes the star is moving directly towards us, but at another point in its orbit, it's going to be moving slightly towards us, but also say slightly to the left, right? And at some point, it's going to be moving entirely to the left, and there's going to be no red shift or blue shift. And so there'll be this variation over time. All right. And then the system itself is moving towards or away from Earth. All right. So that would be a smaller effect, but something to be accounted for. And that would correspond to the whole kind of galactic movement, the fact that stars are always moving relative to each other. So it would be a further correction. So measurements of the orbit size and orbit time from the Doppler shifts tell us about the mass of the stars. So we use the Doppler shift data to get two important values: the orbital size, so the radius, and the orbital time, which is the period. Okay, so why does that work? It works because of the relationship between Kepler's third law and the universal law of gravitation. The fact that we have the p squared and the proportionality to a cubed with the the gravitational expression in there. Let's see, do I have it here? All right, well, I'll show once when we come back from break, I'll remind you of it and show it to you. But I don't want to take time to pull it up at the moment. Okay, but in terms of just Kepler's third law without the universal gravitational point part, it looks like this: p squared proportional to r cubed. And when we turn into an equation, that's the key, because when we turn into an equation, the constant that shows up in front of r cubed, and that's what I want to check for myself, because I have to check it doesn't show up in front of the p squared, at least which form of it, has the universal gravitational constant, big G, and it's got the sum of the masses, m1 plus m2. All right, and that is crucial because it's got a 4 pi squared in there as well. But the fact that it has the sum of the masses is why this matters so much, because it lets us find the mass of the stars. And it has to be sum, by the way, because although when we used Kepler's third law combined with universal gravitation for planets orbiting the sun, we could just ignore the mass of the planet because it was so small. But in a binary star system where both stars are similar in mass, we can't ignore either of their masses, so we have to take the sum of their masses. Okay, we can use the same technique of spectroscopic analysis to analyze planets orbiting stars. All right, and in that case, there would only be one oscillating spectral line, just that of the star, because the reflected light off the planet is way too dim to see. And so just be the small wobble that the planet causes the star to undergo. And what I mean by that is every planet causes the star it orbits to wobble, an immeasurable amount. And since spectroscopic analysis can measure very small wobbles, we can absolutely find out what planets orbit other stars by looking at their red shift and blue shift as they're pulled one way or another by a planet that orbits. If the planet is really small, the wobble might be too small to measure. For example, the wobble induced on our own sun from Pluto would probably be not measured by aliens in another star system, but the wobble induced from our own planet Earth would be easily measured by aliens with comparable techniques that are located around some other star. And we do it for our neighboring stars. Okay, so let's look at not the HR diagram, but a diagram that contains a lot of similar information. This is a graph that shows the mass luminosity relationship of stars. Okay, so this is showing a correlation between a large population of stars, and specifically those main sequence stars we keep talking about, which is, just remember that if you're not told otherwise, you're talking about a main sequence star. If I say, if the slides say, if a discussion question says a star, they mean a main sequence star. Usually it is specified, but every so often it's not. And then you got to remember, well, then it's going to be main sequence by default. Okay, that's the vast majority of stars. So what's the correlation, the relationship between mass and luminosity? Well, mass correlates with both radius. So, more massive stars are bigger, no surprise there. And also corresponds to more luminous. And luminous means brightness. It's literally watts, joules per second. And we don't usually put it in those base units. Instead, we compare it to the luminosity of the sun, which, if you remember, was 46 times 10 to the 30 watts. That was the sun's luminosity. And that's, of course, coming from burning 5 tons of hydrogen per second, or actually 5,000 tons. So that's what L sun is, right? If we were to convert it to base units. But this graph right here, all the values in the vertical axis are multiples of the sun's luminosity. So 1 would correspond to a star that is exactly as bright as the sun. And this brightness that we're referring to isn't a perceived brightness. It's not that apparent magnitude or anything like that. It's not how bright you appear at a certain distance or even a special distance, which is the case of absolute magnitude. But instead, it's just how much actual power that star outputs. So it'd be like if you were able to wrap something around it and measure all the energy coming out. That's what luminosity represents. So this, of course, here at 100 is a star that's 100 times brighter. Here we have a star that's 10,000 times brighter, or even a star that is 1,000,000 times brighter. So we can see just by looking at the value here and remembering that these dots actually represent observed stars. This is real data, that there are some really bright stars out there. There are stars that are almost 1,000,000 times more luminous than the sun. There are also some stars that are dimmer, right? Up to 100 times dimmer. And these big stars, which are the more massive ones, the heavy ones, they're the ones that are brighter. So the relationship is essentially linear, but only when we put it with a logarithm on one side and basically a non-logarithmic scale on the other. So in other words, it looks linear because of the graphs, the axes that we've chosen. But remember that the steps on the vertical axis are not, linear steps. They're not evenly spaced. Instead, they're what's called a logarithmic representation because they're powers of 10. And over here on the horizontal axis, it's not quite linear either. It's closer though. But it also, look at the difference between 0.2 and 0.5, right? Well, okay, that's, that gap there. But then we go over here and then we got 10 to 20. So this is just a less dramatic logarithmic scale on the horizontal axis. So if we were to show this relationship on a graph that had non-logarithmic axes, you know what it looked like? It looked like an exponential function. So it'd be this steep curve. And that's because of the particular power relationship between them. Okay, but all that aside, the clear trend is that the bigger you are, the brighter you are, if you're a star. So a star with a mass of twice the sun's mass has a luminosity of about what? So here you're just reading the graph. Imagine drawing a straight line and finding where it intercepts the data. So who can answer this? Star with a mass, twice the sun's mass. Remember, this 1 is the sun's mass. How luminous would it be? Okay, so I got 2 votes for 2. Let's see. So I'd imagine drawing a straight line, vertical line, right? So that's just starting out with the information that we're given. Then it hits the data, and that means I'm going to draw a horizontal line from there over to here. Okay. So where is this? So this is a tricky thing about these graphs because what does this mean, right? Because it's kind of like it's closer to the 100, right? But it's kind of like halfway between the 1 and the 100. So how do you read that, right? Like, how do logarithmic scales work? Well, they end up working in a way which we can actually kind of see with over here that they have spacing where like this would be the 5,000, which is about halfway. And then the 6,000 is like closer, and then the 7, 8, 9, and then finally the 10,000. So they all get clustered towards the end. And that's just the way the math works out. So it's always a big, like if you're going, it's power of 10 difference, right? And actually in this case, it's 2 powers of 10. So it's 2 powers of 10 difference. And so when you go up that step, the clustering works out like this. I don't know if you've seen, I've kind of seen them a lot before. Yeah, so it seems like it's going to have to be 3 for our answer here. So 50. So it corresponds to about 50. If it was like right here, that would be like, that would be like 90. So it's kind of the way it works out. And here's the strange thing, right? Because that almost seems intuitive, right? Because about halfway is 50, most of the way is 90. But what if it's like right here, right? Well, if it's pretty close to the 1, it's still not like, that doesn't mean it's 10, right? It actually, if it's really close down here, it might only be like 5 because the spacing is not even. That's the whole thing about these scales. Sometimes the logarithmic graphs and ones I put on tests before and similar concept questions will actually show what are called the smaller tick marks to help with reading it. This one does not. So there you go. Their lines were a little bit more accurate than mine. If you want to look into this topic, like look up a video.
Wouldn't that mean the star is more massive?
It would mean it's so we're told it's more massive and asked about its luminosity.
Okay.
So it's twice as massive,
Yeah.
therefore 50 times as luminous.
Okay.
Does that make sense?
It does. I'm gonna have to like write it down and then like
Yeah.
I'm gonna have to, yeah. Okay. Thank you.
Yeah, and this is just a new rule that we're seeing here. This is a law, if you will, that doesn't have a special name that relates stellar mass to stellar luminosity, and it literally follows this graph. And
So it's the meet point and it's like rounding it off.
yes, it's
Okay.
approximating, and it's exactly it's finding where they meet. It was drawing a
Okay,
vertical
got it.
line. Yep. And if you want to review logarithmic graphs, look up a video like, logarithmic graph, understanding logarithmic graphs. And that if that's giving you a lot of trouble, there's tons of short videos out there with some good summaries. All right, so far we've talked about visual binaries and spectroscopic binaries. There's another type called an eclipsing binary. Okay, so we're talking about all these different types of binary star systems, but we're not talking about like, you might have noticed, right? We're not like talking about like stars in like the sense of like, hey, this is their life cycle, this is what they do. We keep getting back to these like kind of like either measurement techniques or like weird mathematical relationships. And I just want to make it clear that there's a reason for that. This is because we're trying to lay the foundation of how astronomers actually know what they know, which is a totally fair thing to try to teach, right? Because it almost seems like voodoo or witchcraft that astronomers can like determine the mass of a star. How would they know such a thing? Well, it's from these types of techniques. It's from using the Doppler effect on a spectroscopic binary and therefore applying known velocities to a law that's well established, Kepler's law combined with universal gravitation, to calculate mass. So if it wasn't for that, if it wasn't for that, the technique, the connections, the established laws, we wouldn't know the mass of stars. Okay, so similarly, and for kind of like hopefully the same, like you think that this is the same. We're talking about this for the same reason. We're trying to understand the methods of measurement. A binary star system. First of all, what is it? Okay, well, eclipsing binary. We already know what a binary is. An eclipsing binary star system is any binary, visual or spectroscopic, where the stars cross in front of each other. Okay, from our viewpoint. So what needs to happen for an eclipsing binary is some sort of eclipse. We have to have one star literally pass in front of the other. So if we think of, this is us on Earth down here, and we are viewing a system with an edge-on view and a top view. So from the edge-on view, we're going to see initially the star is off to the side. From the top view, it's also off to the side. Basically, they look the same. But notice the difference. On the edge-on view, right? This couldn't be the same star system, right? But unless we went to some other place in the galaxy, right? So this is, but like maybe you could think of the top view is Earth's view, and the edge-on view is some alien that lives around some other sun, some other star. But the point is, or maybe these are just different star systems that are comparable otherwise. But notice, right? Top view, it's literally just the small star orbiting the big star. I just wanted to kind of go through and show. But on the edge-on view, we can't see that, right? It's literally the difference between like if you had like two balls on a table, right? And you looked directly down and you moved, you kept one in place by holding it in place with your fingers of your left hand, and you took your right hand and you moved the other one in a circle around the fixed ball, and you looked straight down on the table, you'd see the top view, right? Minus your hands. But if you instead lowered yourself down and kneeled in front of the table and looked straight on so that your eyes were just looking above the edge of the table and you could see the balls, right? Well, then you would see something that looked like the edge-on view, right? You'd be able to notice the distance because, we've got the two eyes and we can tell how far away things are. But when something is as far away as a star, it really looks like they're just moving straight side to side. There's no obvious, depth perception, right? So our edge-on view looks quite different than the top view, even though it's the same actual motion. And this case of edge-on view would be an eclipsing binary because the blue star passed right behind the red star. And then after another half orbit, or well, not red, yellow, passes right in front of the yellow star. So to show it again, okay, top view, blue star passes behind, it's hidden by the big yellow star. Then further in the orbit, passes in front, looks like this. So this would be a great example of an eclipsing binary because it serves two purposes. It shows what the light looks like when it's all coming from one star and the other star has been removed completely and its light is no longer reaching Earth. In this case, it would be the light of the blue star. And then later on, it shows what happens when some of the yellow star is covered and replaced by maybe the more intense, blue light. And then, what is the sum of those? And then compare that to any of the points where they're not in front of each other, and then we can reason out which light comes from each of them individually. Because you've got the two cases where one is eclipsed by the other, and then vice versa. And then any point where they're not eclipsing each other, and you compare those three sets of luminosities, and they can tell you a lot about the stars. Okay? We look at the light curve, the graph of the amount of light collected from a star. Okay? This technique also works for planets, but only one drop in intensity per orbit. With some planets, like really hot, not just hot, but really large gas giants, we actually do see a drop because of the reflected light being eliminated. So there actually can be a secondary small drop, but it's usually just one big drop. So this is what the light curve would look like. Okay, so this is the idea. And the vertical axis here is just going to be the light that we're receiving from these stars. So this is just received light. It would probably be intensity, which is a watts per square meter, and depending on the size of our sensor. And then the vertical axis is just time. Okay, so same eclipsing binary. At this point, this is our like kind of baseline intensity, which is the sum of the light coming from the two stars, because neither of them is covered, right? And now we're going to have the case where the smaller star goes in front of the big one. This causes a drop because some of the light is being obscured. We're losing some of the light from the bigger star. Okay? And so even though, that we're still getting all the light from the small star, the amount that's being covered by that small star does cause a drop in the total intensity. So there we go. All right. And now we continue with our orbit until we get to the point where the blue one goes behind and there's a bigger drop. Why? Because when the blue star goes behind, we lose all the light from the blue star instead of just some of the light from the yellow because of their relative sizes. So check that out. You got two different drops in the light curve. Well, the information from them can be used to actually find the size of the stars. Because if you already know something about their luminosity because you were able to determine their temperature from their color, then you can use that to say, okay, well, this is how intense they are, and this is how much light got covered. Well, now I know their sizes. And you might already know their masses from a Doppler measurement. Well, that's pretty remarkable. You've learned everything about these stars. You've learned how big they are, how massive they are. You already know how hot they are because of that law we talked about way back in chapter 5 that directly relates color to temperature. So all these key aspects of the star you already know. In terms of knowing its true luminosity, we haven't established how we know that yet. Okay, but this does give us relative luminosity, gives us mass, radius of the orbit, size of the star. Lots of information. Okay, and that is a great chance to take a break. So let's take our mid-lecture break. Okay, so looking at a summary of what we've been talking about these binary systems and the different types and what the different types tell us. All right, so I skipped another activity. All right, so Doppler shift in binary systems. Okay, so that's where we look at the different motion and the different change in the spectra. So we see red shifts, blue shifts. So in this case, both would be happening, right? This star would be red shifted at this moment in their respective orbits. The other star would be blue shifted. If you wonder about the orbit, this is like they're orbiting around a shared center of mass, but one's much smaller. So like the center of their orbit is there, see? So like they orbit like this. Basically, they almost orbit like one circle around the other, but they're not like exactly centered. So it's like two elliptical orbits, and because of the rules of ellipses, they have to be off center like this. So that that way the center of mass is the focus of, is one of the foci of both ellipses, as it has to be. All right, so there's 2 points or 3 points in their orbit. So no shifts at all because both their motion is lateral. Right here, they switched. Now the larger one is blue shifted and the smaller star is red shifted. So then if you looked at, we already talked about this, about the binary, right? And it pointed out that you can then calculate the diameter because of the speed and the time to move, right? So you can actually use the width of the drop to calculate the diameter if you know everything else. All right. And then you can find the diameter of the other star by finding just the time of the drop, because that was the whole time it took for it to disappear behind the larger star. So that's how we get measurements of size. over many orbits. Also get the period of the orbit. You can get the period of the orbit from the Doppler as well. So which star is more luminous, the small blue star or the larger yellow star? And the colors do not indicate realistic star color. Instead, the change in luminosity is just just based off of what we know from the graph. All right. So we know that when the blue star is completely hidden, there is this big drop. When some of the yellow star is covered up, there's this amount of proportional drop. Well, if you think about only some of the yellow star is covered, and this is the size of the drop, so that means that the smaller blue star in this case is the one that they're saying is more luminous. Nah, it depends, right? If you like multiply this over the whole area, you actually might find that the more luminous one, just based off of their own graph, could be the larger one. So I'd say it's not as conclusive as the authors intended. So don't worry about this one. Okay. Good simulation here. All right, so those binary star systems are a tool astronomers use to determine important criteria about stars, namely their mass and their size. Okay? And this means that now we kind of have some explanation of how we know these quantities, mass and size of stars. Because stars are far away and there's little dots in the sky. So it's pretty clever that astronomers have worked out ways of determining quantities that are not easy to measure. Okay? So then we go back to the all-important HR diagram, what I described as the equivalent of the periodic table to chemistry, but this one for astronomy. All right? So looking at this graph, luminosity on the vertical axis, temperature on the horizontal, on which side of the diagram is the temperature higher? I actually purposely didn't call attention to this when we first saw the HR diagram yesterday, but did anybody notice on which side of the diagram is the temperature higher? The left or the right? It's the horizontal axis, but are the high temperatures over here on the left, or are the high temperatures, further to the right? Okay, we have a thumbs down for right. Anybody else? Left, okay. So one vote for each. Well, Isabel, you're right. It's towards the left, which is weird because that's not the way most graphs work, right? Most of the time, bigger values are to the right. But the HR diagram is essentially switched. And it's a good reason for it. It's so that we, kind of how the data is presented and also historically the way it was represented. So it's just something you have to get used to. So if you look now, you can see, right, the arrow for the temperature, it's pointing towards the left, showing bigger values or growth in temperature towards the left. All right, then luminosity, of course, grows as you move upwards. I say of course, but I guess it could be opposite as well. So we're almost like we're reading right to left instead of reading left to right when it comes to temperature. Okay. So a note about other aspects of the diagram now that we've established the axes. Again, luminosity on the vertical, temperature on the horizontal. We're going to use this symbol when we talk about anything related to the sun. So if we talk about the mass of the sun, it's going to be M with that little circle with a dot in it in the subscript. In this case, it's the luminosity of the sun. I mentioned before, right, that luminosity is measured in watts, but for comparative sake, we're going to represent it as multiples of the sun's luminosity. So you could write it out as L sun, but very often the symbol is used instead. There are symbols for all the planets also that sometimes get used when we're talking about the solar system, but not as often. This symbol for the sun is widely used, especially for stellar astronomy and talking about other stars. So here we have a range of luminosity going up to stars that are 100 times as luminous as the sun. So not the absolute upper range, but also shown here we have a linear different distance. We'll come back to that. Okay, it won't work. So because if we compare between 20 and 100, it's not going to show enough stars. We need to have a much bigger range. So we're going to replace the linear scale with the scale I talked about before, the logarithmic scale, which is all powers of 10. So that way we can have the lowest tick mark here be 10 to the negative 4, or a star that is a 10,000th as luminous as the sun, 10 to the 0, which is just 1, which is exactly equal to the luminosity of the sun. So the sun itself would have this vertical value, and then go all the way up to stars that are 10,000 times or more as luminous as the sun. So the logarithmic scale is necessary because of the wide range of values. So here we have two stars, a star shown in blue and another star shown in yellow. So how many more times luminous is the yellow cooler star compared to the blue hotter star? In this case, these are not typical stars so much, but we're just asking about a comparison here. So you just need to read off their luminous values, their luminosity values. It is true that the blue star would be hotter, but it's unusual to have them positioned this way, but not impossible, just unusual. So what do you think? How many more times luminous is the yellow cooler star? Okay, Alara says one times more luminous. Oh, no, one, okay, 20 times more, okay. Yeah, that makes sense. 40 times more, okay. So I was gonna draw something on too. Let's see if this would help. So I look at draw a horizontal line for both of them, find out where that line intercepts the vertical axis, which of course is the luminosity axis. And I'm like, okay, well then 10 to the negative 2 is the relative luminosity, relative to the sun for the blue one. 10 to the 2 is the relative luminosity for the yellow one. So what's the difference then? What's the difference between 10 to the 2 and 10 to the negative 2? Okay. Interesting. So this is math here, tricky math, okay? Because we want the how many more times. So it's literally asking for if we call this one like, Y for yellow. So it'd be like LY over LB for blue. Okay? So Y for yellow, B for blue. So that's what it means to have ask for how many times, right? It's the fraction, it's the ratio. And we know the yellow one's brighter because it's got a bigger value, higher up the vertical axis. So then we just put in their numbers, okay? So we literally just would put them in, one in the numerator, one in the denominator. So 10 to the 2 divided by 10 to the negative 2. Okay? So what is that, right? Well, now we're going to use the laws of exponents. I know, kind of groan when you hear that. And the laws of exponents, well, when you divide by an exponent, or you divide by something that has the same base, that's the same as subtracting that exponent in the exponent place. So in other words, 10 to the 2 divided by 10 to the negative 2 is equivalent to 10 raised to the 2 minus negative 2 power. And if I subtract a negative, that's the same as adding. So that means I get my answer is 10 to the 4. And 10 to the 4 is just 10,000. So the answer is 10,000. Easy, right? Maybe. Yeah, it is. I mean, that's a good word for it. Maybe you're being diplomatic, but maybe honest, right? Because it is kind of interesting. Maybe it looks familiar, right? If you working with exponents, um, probably had to do it in math class at some point. And really, kind of the takeaway is that this is why we use a logarithmic scale, right? This is what it all means. The differences are big. The stars vary vastly in how bright they are, how luminous they are. So getting a big number like this is kind of what we should expect because we had to use a logarithmic scale. That makes sense. All right, and this is sort of showing the calculation. 10 to the 4 is the difference. I'll erase my work so you can see it. Okay, so 10 to the 4, that is the difference between those two values. And then I showed where it came from. Of course, 10 to the 4 is just 10,000. Okay, oh, this shows the answer. Right. So temperature axis. The temperatures don't vary as much. So the scale on the temperature axis is not linear, but it's not powers of 10 either. So it is technically a logarithmic scale, but not as dramatic. All right. So it's also not linear. And you can tell, right, because it's like 3,000 to 6,000, and 6 to 10, and then 25,000 is over here. So I mean, think about this. Like this is a difference of 15,000 Kelvin, but that's a smaller gap between these two, where the difference is 3,000 Kelvin. So it's clearly not linear. All right. But like I said, it doesn't have to be powers of 10 either, because that would be too much. So instead, it's a different base than 10. Don't worry about what it is. It'll always just be represented as numbers like this. But do note that don't expect them to be evenly spaced. The other way that the other way the horizontal axis is expressed is with letters that correspond to the spectral class. Okay, so pause. This is important. Temperature and spectral class are equivalent. They are literally just two ways to say the same exact thing. So if you know temperature, you know spectral class, and vice versa. So absolutely equivalent. Okay, so this is one way to show it in Kelvin. This is in spectral class. You might even wonder why bother having these weird letters that correspond to different temperatures. The reason is truly just historical significance. This is the way that the stars were grouped initially before scientists even knew that they related to temperatures. So the letters predate the knowledge about temperatures, and they're still widely used. That's why we teach them. Okay, so here's the temperatures overlaid on the spectral classes. The spectral class letters in descending temperature order are O, so those are the hottest, B, A, F, G, K, M, right down to M being the coldest. All right. And the way that I remember it is silly mnemonic device. I don't think it's terribly inappropriate or anything. It's just sort of silly. And it's only boys accepting feminism get kissed meaningfully. Easy to remember, right? Because it's sort of strange. And when you remember the phrase, you remember the letters. O, B, A, F, G, K, M. There's lots of other phrases. You can look them up online. Okay? It's a mnemonic device. Okay? So there you go. Back to using the temperatures, although we'll talk more about spectral classes in just a minute. Now let's populate it. Okay? So we've established the axes thoroughly, I hope. So now let's actually put stars on there, and we just did. Okay? So this is kind of what the HR diagram looks like once data is put into it. So imagine that this is, a bunch of collected data from observed stars in the Milky Way. And it would apply to stars in any galaxy, really. There's no significant difference. And it's showing some, different groupings. One that you might recognize already is the main sequence. So we can see the main sequence of stars. This big group kind of right in the middle. And the slides will circle them as well. But this is I just wanted to point out, this is the one we've seen before, and we've seen the name, the main sequence. It is like a diagonal swath, right, from the upper hand corner, which is the most luminous and hottest stars, the upper left-hand corner, down to the lower right-hand corner, which are the dimmest, in other words, least luminous and coolest stars. In terms of color, check it out. They vary from the bluest all the way almost to ultraviolet, at the very bluest, the hottest, down to red stars. And before, we talked about dwarf stars and whether or not they're stars, and I said that white dwarfs aren't, but red dwarfs are. Well, these are those red dwarfs down here, kind of this whole region. All right. Interestingly, these are the white dwarfs down here. All right. And when we got some giants over here, these are called red giants. And then these are supergiants. Okay. I'm not putting the names in because you're going to see them in the slides in just a second. But these are all the different groupings of stars. Okay. Often it's put on a black background because that way you can show the colors, right? So we can actually see the colors of the stars from the red ones down here up to the blue and so on. Right? Lots of good videos to introduce it, lots of resources online. All right, so now let's talk about those different types of stars. Okay, so HR diagram, the most powerful reference in astronomy. All right, so first, let's test your understanding. Which of these two groups of stars have a larger radius? The ones shown down here or the ones up there? Radius obviously isn't one of the axes. So how would you make a reasonable guess here? Which stars have a larger radius? Think about the way the two groups overlap in temperature a bit. So if there's some overlap in temperature, but the difference in luminosity is dramatic, what does that suggest about size? What does it suggest about size? All right, sorry, I had to step away for a second. I'm back. Okay, so anybody have a good guess? Okay, so maybe it was which ones are larger? So the guess was that maybe the ones that are down, the less luminous ones are the bigger ones, that they're also hotter. Okay, let's see. So it turns out that that's not the case. And it was difficult to reason out. It really kind of came down to some pretty subtle connections, like ones that I've gotten used to, but I totally understand are not obvious. And that's okay, well, if there is some overlap in temperature, then, and you think about how temperature is related to energy, then the only way that these ones can be so much brighter right? They can output so much more power is if they have just more area for that energy to come, to radiate from. So that's why these ones have to be bigger, the green group, which is the thumbs down group. And it turns out that the relationship is pretty straightforward, that when you look at the HR diagram, radius moves as a diagonal from the lower left-hand corner, up towards the right. So in this direction, you have lines that correspond to progressively bigger radii. So, you might have, like, if you compare to the size of the sun, then the radius would go up, logarithmically. So steps of 10, powers of 10, in terms of, stars that are, 100 times smaller than the sun, and so on, as we move up. And each of these diagonal lines would correspond to that next multiple of the size of the sun. Okay, so now main sequence, saw it back in chapter 16 very briefly. It's the most important grouping of stars on the HR diagram, as I've said like 10 times. And the reason it's so important is because most stars spend their lives on the main sequence. And, not their whole life. There's always some point where they're going to go off the main sequence, but they spend most of their lives on the main sequence. So you could say stars spend most of their lives, might be a better sentence. So in other words, if you look up at the sky, the vast majority of stars you see in the sky are going to be main sequence stars, just by the law of odds, okay? It's just statistically they have to be. The relationship of main sequence stars to mass is the following. As you move up and to the left, you have increasing mass. So you have stars down here that have masses that are less than 100th the mass of the sun, up to here where you have stars that have masses that are over 300 times the mass of the sun. So this might be 300 times the mass of the sun. You use that notation, right? Circle the dot in the middle, and down here, just 100th the mass of the sun. This relationship between the HR diagram and the masses, star masses, only applies to main sequence stars. So unlike when we talked about radius and we drew an arrow over the entire HR diagram, right? So over here, the larger radius applied to all types of stars, not just main sequence. And that's absolutely true, no exceptions. This relationship between mass and luminosity and temperature, because that's what this is. This is taking the three variables and relating them. Well, it only applies to main sequence stars. So in other words, the rules for mass when it comes to the non-main sequence stars, these other types of stars, they're not as straightforward, and there's not going to be one rule. But luckily, since most stars are main sequence, it's still an important rule. All right, so now the actual names. Okay, so far, main sequence. Within the main sequence, so a subcategory of main sequence stars are red dwarfs. In other words, all red dwarfs are main sequence, but not all main sequence stars are red dwarfs. Okay? Then stellar ages, also a rule that only applies to main sequence because it only makes sense to talk about lifespan, which is how long the star has to live, if you're talking about the main sequence. Because as soon as a star leaves the main sequence, it's dying. When stars are born, they're born onto the main sequence. So that means that they're really their whole prime of life is the main sequence, and it's the only time we actually relate star lifespan to other quantities. And the relationship is basically going to totally overlap with mass, because just like mass, it only applies to the main sequence, but for a very direct reason. And it's you're going to have except it's reversed, because the very low mass stars live the longest and the very high mass stars, which are also the very luminous, high temperature stars, live the shortest amount of time. And in terms of the actual ages, live a long time. What is a long time? Well, a long time is really, at least for stars, and I don't know if it will seem short for you, but it's only about 100 million years. So it'd be about 100 and then million years. Sorry that the green on purple doesn't show up as much as I wanted. Okay, so 100 million years. And I mean, that's just, like a tenth, and sometimes some of them only live like 60 million. So, I mean, think that's a tenth of a billion, right? That's a very, very short lifespan. That if a star only lived 100 million years, the planets wouldn't even be fully formed by the time the star dies. The process of planetesimal accretion that we talked about when we talked about solar system formation takes longer than 100 million years. It takes about 200 million on average, right? And it's not an exact thing. So, but certainly, I mean, once you get down to such short lifespans, you have no chance of life because planets that never even have time to form. Okay. Obviously, our sun has a lifespan in about 10 billion years. And then when you get down to these ones, you have lifespans that are around 1 trillion years. And obviously, that's just based off of kind of measuring how the rate at which they're changing currently, because 1 trillion years is so much longer than the current age of the universe. The universe is only about 15 billion years since the Big Bang. 1 trillion is 1,000 billion. So these stars have a long time to go. And based off of how stable they are and how long they live, they give a strange implication that the universe is apparently really young. If the universe is populated by stars that have the capability of living 1 trillion years, but yet it's only 15 billion years old, that means that we happen to be alive at a moment when the universe is super young. Weird, right? All right. So, right, they're pointing out 100 to 1,000 billion. 1,000 billion is 1 trillion. All right. And then millions, as I said. Okay. So, main sequence stars, the only subgroup that we've identified by name is red dwarf. That's basically the only significant subgroup of main sequence stars. Sometimes sometimes over here, these ones are called like blue giants, but that's not less often used. But now some other important terms of stars that are not main sequence stars. Giant stars. Okay. In terms of giant star evolution, stars leave the main sequence to become giant stars. As I said, this is a process where they are running out of fuel and they are ending their lives. Dying stages of middle mass main sequence stars become giants. Okay. Then there's the supergiants. Now, often the term red is put in there. So you got red giant, red supergiant, but they're not strictly necessary. But if you remember, I used that before. Okay, so supergiants are this next group. So remember, the giants are kind of this grouping here, and you can tell that they're separate, right? And and there's empty space in between because there's only so many processes, only so many types of stars. So we don't find stars that have this combination of temperature and luminosity, like, where there's a gap. Okay, but on to supergiants. Where do they come from? Well, they are, stars that evolved from high mass stars. So the really big main sequence stars, the ones that don't live very long, when they leave the main sequence, when they run out of hydrogen to fuse into helium, they become supergiants. Finally, there are white dwarfs, which are not stars at all, but are stellar corpses. They're the corpses of stars, or they're sometimes called stellar remnants. And so what happens is your red dwarfs become white dwarfs, and also giant stars become white dwarfs. This process here is more theoretical than anything because none of the red dwarfs have had time to become white dwarfs yet. but it is speculated that that's what happens. They gradually just sort of cool into white dwarfs over hundreds of billions of years, at least tens or hundreds of billions. But this process is known and we've observed lots of intermediate cases of giant stars becoming white dwarfs because that process only takes about 10 billion years. And so we could actually see examples by looking further away and therefore looking back in time. Right? And also just because of the population of stars that exist in the Milky Way galaxy and the fact that the Milky Way galaxy is about 12 billion years old. So it's old enough to contain stars that have already gone from the main sequence to the white dwarf phase. So the white dwarf are mostly dead, low and middle mass stars, mostly in terms of the fact they're still bright, but entirely in that they have no fusion. The source of their light, because they are fairly bright, is entirely from just leftover heat. They are just gradually cooling. They're no longer creating light through fusion. It's just residual heat from the contraction that caused them to be made because they're incredibly high density. They're tiny. Okay? A typical white dwarf is the size of Earth. So a typical white dwarf is the size of Earth, but has a mass that is around the mass of the sun. So you have a mass that is, anywhere from about 70% to 1.5 times the mass of the sun, 1.4, but the size of the planet Earth. So this is a incredibly dense object, the white dwarf, which is why they can be so hot and relatively bright without fusion. If you're wondering what happens to the supergiants, well, that's where the really cool stuff comes from, the things that fascinate many astronomy students, because they become neutron stars if they're big but not really big. And if they are really big, technical term, they actually become black holes. So there's a cutoff between mass required to become a neutron star and becoming a black hole. So the biggest, most massive stars become black holes when they die, and their death is also itself quite dramatic because it results in a supernova. Beyond stars, so another example of a non-star, and the third type of dwarf is something called a brown dwarf. These are similar composition to stars, but too small to start nuclear reactions. So they're significantly bigger than Jovian planets. They're bigger than gas giants by, like quite a bit, like, maybe 20 times bigger than Jupiter. So they have very unique characteristics, but they're not stars either. Okay? They're brown dwarfs. They're quite common throughout the galaxy, but they fall into a strange gray area or a brown area. All right, check time. Good. Okay, so there you go. Types of stars. Great kind of just run through of the HR diagram. You want to get practice with all the different types, remembering the rules, the relationships, and in the homework you get some practice with like kind of the actual numerical relationships, some of the functions that allow for those curves that we saw, those arrows, like the age arrow, the lifespan arrow, as well as the mass one. They're all exponential functions because remember logarithmic axes. But beyond that, just like like examples of particular stars, more about those life stages, I think will probably drive home the ideas. But now let's review the spectral types. So when we talk about spectral type, it's a 3-part label classifying system. All right, so we have the spectral letter, or the spectral class that has a letter, the temperature ranking, which is a number, and the luminosity class, which is a Roman numeral. Okay, so examples. The sun is a G2V star. Betelgeuse is an M1A star. Okay, and actually it's an M11A star because it's M1 and then the Roman numeral is 1A, and I guess this would be more like G25 because the Roman numeral you'd read it like a letter. rather. You read it like a number. Wrong word. I don't normally read them out loud. Rigel is a B8 1A star. Aldebaran is a K5 3 star. So reading them out loud is not their strong suit. But what you do notice, Roman numeral, okay? The Roman numerals sometimes have a letter attached to them, but they have all exact meanings. So this is the 5 luminosity class, Roman numeral 5. This is the luminosity class 1A, and this one is the luminosity class 3. We'll talk about what those are. The 2, as we learned, is a temperature ranking. So we'll see that in just a moment. And then the spectral class are the letters that we saw on the horizontal axis. Okay, so the ones with the only boys accepting feminism get kissed meaningfully letter system. All right, so let's look at the sun and break down these different letters. What do they mean? All right. So first, let's see if you can answer the question. Spectral class is determined by what? So spectral class, temperature, apparent magnitude, spectral appearance, atomic composition, or distance from Earth. What does spectral class tell you? Remember that spectral class, right, is the letter. Luminosity class is the Roman numeral. So when you say spectral class, we're just talking about the underlying letter. So what is it? Temperature, apparent magnitude, appearance, atomic composition, or distance? All right, got one vote so far. Anybody else? All right. Well, you special appearance. Wait, what? Oh, okay. I would have said temperature too, but I get what they're saying. It's something I hadn't mentioned yet. I wasn't planning on like kind of getting into, but it's true that they correspond to particular signals that are found from the different types of stars. So there's certain spectral lines and there are emission lines of atoms that end up in the atmospheres of different stars, and different stars have different atoms that end up in the atmospheres. But it ends up being a stand-in for temperature, which is why when I described that, I said, oh, hey, just, it's just temperature. But I guess strictly speaking, it's not. So yeah, it's a fair point, but it's just, it adds to an already complex system. But as you saw, the horizontal axis on the HR diagram can be expressed either way, literally with temperature or spectral class. So every spectral class does have a temperature range. That's true. That hasn't changed. It's just that they're where those lines are, like the dividing line between like the O and the B, comes from the different emissions. That's why they decided to make the line. They didn't decide to make the line because it corresponds to 27,000 Kelvin. The line is there because of the different emissions. So in that respect, this answer is unequivocally correct, but not what I was talking about before. And like I said, wasn't on the front of my mind, which I apologize for. I didn't mean to lead you astray. There's a good figure that shows like kind of the different, they're all kind of like various exotic molecules and atoms that exist in the atmospheres and which one is associated with each spectral class. But at least, not that you need to know the actual, what those different spectral lines are, but just you can see kind of what it means to split them up that way. All right, but here they are, O, B, A, F, G, K, M. So G is right here. Yeah. So corresponding to that spectral class, which does have a temperature range, but the divisions are set by emission lines. Okay, so then the temperature ranking tells how hot compared to other stars of the same spectral class. So this is a subcategory within Gs. So if you look at G2, and don't worry about answering this one, I'm going to give you the answer. So it asks which is hotter, a G0 star or a G9 star, and it's actually the G0 star. And the way the ranking works is 2 is the second to the highest. So you have if you moved up, you'd have like G1 stars, and then G0 are the very hottest of that spectral class. So like a G0 star would correspond to 6,000 Kelvin, whereas a G2 corresponds to 5,800 Kelvin, which happens to be the value kind of right here. And about the color that I chose, and for its peak emission line at least, or its peak of its black body continuous spectrum curve. Okay, so there you go. Spectral class, lays on the same axis as temperature, but technically the divisions correspond to different emissions. Won't be required to know what those emissions are. You are not required to know the emissions, but it is good to know that the logic behind the divisions is because of spectral lines. Then within those different classes, so just thinking this right here, right, or it's this one. Within those different classes, as you move from higher temperature to lower temperature, you move from 0 to 9. Okay, so you're moving to higher numbers. But now finally, the last part of the name, the luminosity class. This one is kind of the most straightforward, and it's the most unique because it doesn't just refer to that horizontal axis, which has so many different ways to represent it, right? The horizontal axis almost seems like it's kind of overexpressed, right? But what is luminosity class? So we're told here, it tells us if the star is a supergiant, a giant, or main sequence. So that's what it is. The Roman numerals literally correspond to the different groupings of stars, which are the different life stages of stars, although no one star goes through all of these different luminosity classes. Instead, different mass stars go through different ones, but of course, all stars do start on the main sequence. So every single star that exists will spend most of its life as a Roman numeral 5 luminosity class star. And the terms, remember, it's spectral class are the letters, luminosity class are the Roman numerals. So main sequence are the Roman numeral 5, subgiants, Roman numeral 4, giants, which our star will become, Roman numeral 3, bright giants, Roman numeral 2, less luminous supergiants are the 1Bs, and then the brightest supergiants are the 1As. So if we look at the sun, we can put its luminosity class. We can identify its luminosity class by looking at the fact that it's on the main sequence, which means it's going to be right here, right? So 5 means that it's in this purple bubble here, this purple section, because that's the main sequence, luminosity class 5. So there you go. So everything that we specified puts us right in this range. All right. So then if right, so yep, these are just the different types of giants. So are the supergiants split horizontally or vertically between luminosity class 1A and 1B? Well, they're called brightest and less luminous. So no surprise, the split is horizontal because, of course, the vertical axis is the luminosity axis. I just want to get through the last of the material here as we run out of time. Okay, so looking right here, supergiants, the two subcategories. So this is kind of a summary of the different luminosity classes. See, main sequence, then the subgiants, then you have your what do they call it? So it's giants and bright giants. Check the name. Forget. Yeah, giants and bright giants. So main sequence in the purple, the sort of rusty red are the subgiants. The brownish orange color is the giants. The yellow gold color is the bright giants. Then we have the less luminous supergiants in sort of the blue-green color, and finally, our mossy green color is the bright supergiants. So, which red star could be classified as a K82 star? Because all of these stars are red. Okay? You see all these stars that you could see with a telescope. But which one could possibly be a K82? So what do you think? Okay. Anybody else? I see Alara's answer. I was good too. I was fat. You were on it. You're fast. Makes me think that you're probably understanding it. And so here's K's. So in terms of K8s, basically it has to be 5 or 3. And the 5 is on the main sequence. So that would be a K85. So it's got to be 3. Right? Because that's the one that actually is a bright giant. And honestly, that would have been enough, right? If you looked carefully, because none of the other ones were quite bright giants, but it's hard to tell for sure. So I basically went through the same process that they did, where I kind of looked, at the K's, and I said, okay, well, 8s are going to be to the far right hand side of the K's, and then went from there, narrowed it down to 5 and 3. So with distances, and we'll talk, in fact, the very next chapter, by the way, is going to be all about stellar distances. That's kind of like what we're coming up to. So if these stars all have the same apparent magnitude, which is closest, right? Because think about luminosity. Well, apparent magnitude is how bright something appears. But if you know that star 1 is much more luminous, but appears just as bright as a much less luminous star 3, because luminosity would be like if you could get up close, right? Because it's like the true feature of the star. But if they all appear as bright, well, that means that 3 has to be the closest because it's actually the less luminous. So by being able to identify stars on the HR diagram because of key features of their color and their emission lines, it can start to solve that puzzle of being able to find distance. Because if you know apparent magnitude, which you do know, because you just need to look at the star, then you can find distance if you know true luminosity. On the other hand, maybe it's not distance that you care about. Maybe it's the luminosity that you care about, and you know the distance because you know that star is in a group with another star, right? So you actually know where it is. Well, then you can work the other way. If you have a known distance because of a star cluster usually, then you can then find luminosity class or luminosity or whatever, which can be a confirmation. So essentially there's this almost like grid of interlocking ideas that allow for a logic puzzle-like approach to discerning these key values, these key characteristics of stars. Because I think it's totally fair to say it is not an easy science to study stars. They don't, you can't just go out there and measure them by hand. Okay. So in terms of actually measuring distances, the techniques that are used, and let me check something real fast before we proceed. Yep. So this is not something we're going to talk about now because I knew it's in chapter 19. So this is just sort of showing what we will be talking about. When we talk about stellar distances, and this is sort of setting the stage for it, we're going to talk about a number of techniques that astronomers use. They're going to include this idea of actually referring to the HR diagram, which is called spectral parallax. Kind of a strange name because there's no parallax involved. Actual parallax, which is a literal measurement that involves angular calculations. Radar, which isn't actually used for stars, but is used to create the baseline that's necessary for employing parallax. That sentence makes sense. That's great. If it doesn't, we'll get more into it. We briefly talked about parallax in one of the early chapters. And then finally, there's a very special type of star, kind of a category of stars called Cepheid variables. And they are wonderful for the way that they can let us know luminosity. So this is a way that astronomers can measure luminosity directly, and they don't need to go from apparent magnitude. They can actually look at the period of oscillation of brightness, because this is an unstable type of star, and then based off of a data set that's been established over the years and very, very accurately, obtain the true luminosity of that star. And once you know that, you immediately know the distance. Because, again, like apparent magnitude, apparent brightness is always a measurable quantity. It's just literally just like look at a star, let it hit a light sensor, through a telescope, find out how bright it is, how bright it appears, right? So if you know its true luminosity and you know its apparent brightness, you can calculate distance. All right, this shows the ranges. The ranges are given in parsecs, which is a alternate way of measuring distances, and is equal to about 3 light years. We'll talk more about that. It actually corresponds to a parallax angle of 1 arc second. All right, so obviously a lot to unpack there. And the last thing that we'll say today about making the HR diagram, this is sort of just like the history of putting all this data together. So cataloging light from 2.5 million stars during the 4 years in terms of modern sort of like establishing of the HR diagram, and been around before that, but kind of reached its current level of accuracy in the late 80s, early 90s. All right, there is these ideas of the BV color index. There's some good simulations online that I use in my lab version of this class, or the lab that goes along with this class, measuring brightness of just blue light, and then with V magnitude, this is just looking at all the non-blue light. And so this is a way for astronomers to separate out blue stars from red blue stars and so on. And then they came up with this index, and that helped them establish all the relationships between temperature and color. So larger BV color index meant redder, which meant colder. Obviously, bluer is hotter. So there you go. You won't be responsible for the BV index. We already got enough. So there you go. All about our introduction to the study of stars. Okay, that's where we're at right now. How do we study stars that are so far away and are just tiny little faint dots? Well, maybe you have a better idea now than you did before class started. I hope so. Stop the recording.